Hello, Shahab Ahmed here. The target for today is to clarify all your concepts about chemical kinetics. We'll do that with the help of just 15 MCQs. Then you will have your concept clear about rate of reaction, rate law expression, how to write a rate law expression and what can we deduce from rate law expression, like order of a reaction, unit of K, relation between order and a unit of K. If unit of K is given, how can you find out the order of a reaction? So all these you can do with just the rate law expression. Then you can also find the relationship between K and activation energy. What is the relationship between K and activation energy plus temperature? Then you can also learn about half-life of a reaction, relation of half-life to concentration. So what is the relationship between the initial concentration and half-life of a reaction? So we will give you a short trick to solve MCQs with the help of that. And then in the last but not the least, we will also cover factors affecting rate of reaction like concentration, pressure, temperature, and activation energy. With the help of just these 15 MCQs, we will clarify all your concepts about these, and you will also do practice. So stick around. Oh, you must have read the question. The question is saying the rate law expression for the reaction A goes to C is given as rate is equal to Ka. Then the unit of K will be, so we are given the rate law expression and we are required to find the unit of this thing, the rate constant. The options are per mole dm cube per second, mole per dm cube per second, and per mole dm cube. So as we know that, what is rate? Rate is the change in concentration per unit time. So here in this case, the change in concentration per unit time is equal to the rate constant to the concentration of the reactant power 1. Here power is 1. So now we have to put the units. The unit of concentration is a molarity, mole per dm cube or molarity, and the unit of time is second. If second goes in the numerator, it becomes second inverse. So molarity, second inverse are the units on this side. Here on that side we have K, we have to find the unit of it. The unit of concentration is molarity. So if molarity comes from that side to this side, it becomes molarity inverse or comes in the division. So molarity over molarity per second becomes K. Molarity over molarity cancels out. So the unit of K becomes per second. So option C is the correct answer. Now, what are the other deductions from this rate law expression? Other deductions are, we also got another expression for the rate of reaction. That this also was one of the previous MCQs. It was asked that rate could be represented as, so you must know that rate could be written as change in concentration per unit time. So you must know that this is another MCQs. Then one other MCQs was how we could find the order of reaction. So the order of reaction is the power of concentration in the rate law expression. So if it were 2, 3 or anything in fraction or 0, so or minus the power of the concentration term is the order of reaction. Small trick, with the help of that we could find the order of reaction from the units of K. So the relationship between order of reaction and K, that is molarity (1 minus n per second) is equal to K. What is n? N is the order of reaction, where m is molarity. M is equal to mole per dm cube. If the units of K are given, we can find order of reaction. If order of reaction is given, we can find units of K. Pretty easy. We have looked at the question. It is saying that the unit of rate constant is, the unit is given, mole per dm cube per second. The order of reaction is, the unit of K is given, and we are asked for the order of reaction. In the previous MCQs, we got the shortcut for finding the order from the unit or unit from the order. So and the options are 1, 3, 0, or 2. So you must mark your answer and then we will discuss it over here. Now we will go to the discussion. So as we know that the units of K is equal to molarity 1 minus n, where n is the order of reaction per second. Here m means molarity. What is molarity? Molarity is mole per dm cube. Okay, and per second is also over here. What I have to do is this is equal to this mole per dm cube per second. Here I have to get 1. Okay, to get 1 I have to put n is equal to 0. When n is equal to 0, I'll get 1 in the power of this thing. So 1 minus 0 equals mole per dm cube per second. So I put n is equal to 0. N is equal to 0 means 0 order reaction. And over here is the order of reaction. So if n is equal to 0 means 0 order reaction. 1 mole of a reactant reacts with the rate of 0.6 mole per dm cube per second. What is the rate constant if reaction is first order? So option A is 1 per second, option B is 0.3 per second, option C is 0.6 per second, and option D is 0.9 per second. As we know that rate is equal to K, rate constant, into molarity of the reactant to certain powers. Here the power is 1 because the order of reaction is 1. As we have discussed earlier, that the power of the molarity is the order of the reaction. Here the reaction is first order, so we have to put 1 in the power of the molarity. We just have to put the values in the place of rate. We will put the value of rate, that is 0.6. We are finding K, so K will come in its place, and we can find molarity from number of moles. As 1 mole is given per decimeter cube, so molarity becomes 1. So K is equal to 0.6 per second. Answer is 0.6 per second. Option C. The question is, change in concentration of a reactant is plotted against time and the slope dx over dt is determined. The value of dx over dt are plotted against a minus x squared. A straight line is obtained. It may be concluded that the reaction is dash order, first, second, third, or 0 order. So for the straight line, we must have y is equal to mx in some cases plus c. We know that here in this case y is dx over dt, and m in this case is equal to k, and x in this case is the remaining concentration, a minus x squared. So this becomes the rate law expression, and we know that the power of the concentration in rate law expression is its order. Here the power of the concentration term is 2, means this is second order, so it was quite easy. Rate of change of concentration with respect to concentration square, we will get a straight line for the second order. And the question is saying, why does raising the pressure of a fixed mass of gaseous reactants at constant temperature cause an increase in the rate of reaction? So why, if we increase the pressure on a gas, its reaction rate increases? What is the reason behind this? First of all, mole collision occur is the reason that number of collisions per second increases, or energy of the molecule increases, like more molecule have more than activation energy, or raising the pressure decreases activation energy, or this happens. Now the options are 1, 2, and 3 are correct. All of them happens at the same time. 1 and 2 happens like collision increases, also the energy of the molecule increases. Option C is 2 and 3 are correct, like energy of the molecules increases and activation energy also decreases. Or just one is correct, means number of collisions per second increases. We are given that the temperature remains constant, mean the third one is not happening. More molecules have energy greater than activation energy. So if we are not increasing temperature of the molecules, means the energy of the molecule is not increasing. What happens as a result? When we increase the pressure, the collision of the molecules per second increases. So what about the activation energy? Raising the pressure, does it lowers the activation energy? No, the activation energy depends upon the path of the reaction. As long as the mechanism of the reaction remains the same, there will be no lowering or increasing in the activation energy. So the only option that remains correct is option 1. So option D is the correct option, because increasing the pressure increases the probability of the molecule to collide with one another. So the collision per second of the molecules increases. So the question is saying the log of rate constant of a reaction is directly proportional to temperature change, inversely proportional to temperature change, not affected by temperature change, affected only by activation energy, not temperature. So what are you saying? You must mark your answer and then we will go to its details. So as we know from Arrhenius equation, K is equal to, which is the rate constant? I must write it with a black. K is equal to A E power minus EA over RT. You know the terms in this equation. A is the rate constant, A is the frequency factor, E natural logarithm, EA activation energy, R is ideal gas constant, T is absolute temperature in Kelvin scale. So now if I apply log to both sides, log of K is equal to log of A minus, so if I apply log to E, I'll get 2.303 EA RT. Instead of rearranging, and I will get log of K is equal to minus EA over 2.303 R 1 over T plus log A. So Y equals M, this becomes M, and 1 over T becomes over X, and that log A becomes C. So a straight line equation. But here we have to look for the relationship. The relationship between log of K and 1 over T is, from there I got log of K is inversely proportional to minus 1 over T. Negative inverse relation becomes positive direct relation. So log of K is directly proportional to temperature, means the value of K increases with temperature. As K increases, the rate of reaction also increases. So direct relation between both of them. Okay, the question is saying, which statement correctly describes an effect of temperature on gaseous phase reaction? Which of these statements is correct about temperature effect on a gaseous phase reaction? Number 1, more particles now have energies greater than EA. EA means activation energy. So by increasing temperature, you give the particle more energy, so now more particles have activation energy. Second, the energy distribution profile changes with more particles having the most probable energy. Okay, energy profile shift toward more particle having more probable energy. And number C, EA of the reaction decreases. So by increasing temperature, the activation energy decreased. So you must mark your answer and then we will discuss it. So first of all, more particles now have energies greater than activation energy. Yes, this is correct, because as we know from the Boltzmann distribution, this suppose is T1, and now I have increased the temperature to T2. The curve become smoother, like now the cleft has come down, and suppose this is the point, suppose this is energy, and this is the number of fraction of particles. Okay, so the fraction of particles, and this is energy. Now the area under the curve represents the amount, the number of particles, and x-axis represents the energy, and suppose this point is EA. Now here the amount of particles in the case 1 having the activation energy was this in the blue covered area, but when I increase temperature to T2, the area under the graph now becomes this. So now more particles have activation energy. So this option is correct, but we will look for other options too, because there could be more than one options correct. The energy distribution profile changes with more particles having the most probable energy. Yes, the energy profile change, the energy distribution profile change. Yes, this up to this point, this is correct. With more particles having most probable energy, this could be questioned, because here we can see that with increasing temperature, the particles, the most probable energy, the particles with most probable energy, the cliff, the peak of the cliff came down, the peak of the mount came down. Now we have lesser number of particles having the most probable energy, because this is the fraction of particles. So we have now the lesser amount of particles having most probable energy. So this is wrong. EA of means activation energy of reaction decreases. Now activation energy does not decrease with increasing temperature, so this is wrong. So both of them are wrong. The only correct. Which row correctly describes what happens when the temperature of a chemical reaction is decreased? So temperature is lowered down. Okay, what will happen? The kinetic energy of the particles decreases. And we have discussed earlier, there are two things given: activation energy and successful collisions. So activation energy does not depend upon the temperature, the given temperature, and number of collisions depend upon temperature, because it depends upon the kinetic energy. So with decrease in temperature, we will have decreased kinetic energy and decreased number of collisions. So this could be either this or this could be true. So in this case, they are saying the activation energy decreases, which is a wrong perception, wrong answer. Remains the same. Yes, activation energy remains the same, and the number of successful collision decreases because value of kinetic energy decreases. The addition of a catalyst to a chemical reaction changes. We know the answer to it is the activation energy. Why not the enthalpy or entropy or free energy? Because these are state functions, and they only depend upon the initial and final state of the system. How stronger the bonds are made, how weaker the bonds are broken. So it depends upon the energy changes. And what does the catalyst do? It does not change those things. It just changes, it provides the alternative path for the reaction to happen. And this state function does not depend upon the path followed by the reaction or the system to reach over there. So it just changes the activation energy of the system. So now the molecule with lower energy can also form. For endothermic reaction, we have to mark the activation energy. If the activation energy for forward reaction is greater, or reverse is greater, or both are equal, or none of these is the relation. So we have to draw the energy diagram, the potential energy diagram for both endothermic as well as exothermic reaction. So suppose these are our reactants and these are our products. For endothermic reactions, the product are at a higher energy state than reactants. So our energy profile will go like this. We will have a curve like this. So this is the activation energy, EA, for the forward reaction. In the case of endothermic reaction, okay, with respect to time, what happens? Okay, now, and this is the activation energy for the reverse reaction. So we can see that the activation energy, these are reactants and these are products. So we can see that the activation energy for the forward reaction is very high than the activation energy for the reverse reaction. So we can mark our answer forward reaction higher than reverse reaction. So activation energy for the forward reaction in the case of endothermic is higher than the activation energy of the reverse reaction. So the rate constant for a first order reaction was found to be 0.2 seconds. What will be its half-life? So for the first order kinetics, we have to find the half-life of the reaction if the value of K is 0.2 second. So 10 second, 5 second, 3.5 second, or 15 second. You have to calculate it yourself. Now mark your answer. I hope you have marked correct answer. As we know that for first order kinetics, we know that the half-life of first order kinetics is independent of initial concentration. It depends upon the value of K. So it is 0.692 or 3 divided by K. So we can round it up to 0.7. Okay. Now we have to divide 0.7 by the value of K, that is 0.2. So point goes with point, and 7 divided by 2 is round about or exactly 3.5. So we will get 3.5 seconds. So half